So welcome everyone. So in this video we are going to see about minimization of Boolean functions and digital circuits. So Boolean functions are used to represent logical expressions in terms of sum of minterms or product of max terms, in short SOP and POS. So number of these literals increases as the complexity of digital circuit increases, which leads to large and inefficient circuits. So that is if consider an expression like a bar b plus a c b bar. So here this term this called literal, this another literal. So in this function there are two literals. So if number of literals or number of input variable increases, then this leads to inefficient circuits. So if you are designing as it is, we have to simplify this function and we have to implement. So by minimizing Boolean functions, we can reduce the number of logic gates, and which will improve the performance in terms of speed, cost and power consumption. So if you are reducing the number of functions or number of literal in the actual function, so the number of gates will reduce automatically, which will reduce the area and power consumption. So for reducing Boolean functions, there are different techniques. The basic technique is Boolean postulates and Boolean theorems and Boolean laws. So there are different Boolean postulates and laws. So in which there are identity law and null law, idempotent law, complement law, domination law, double negation law, distributive law. These are all very important. De Morgan's law, absorption law and complementation law and consensus theorem. For example, if you consider De Morgan's theorem, so we can write, if the function is a dot b the whole bar, then we can write as a bar plus b bar, both are equal. So by using complement law, we can write, if in the given function if there exists a dot a dash, we can write as 0. By using identity law, a dot 1 equal to a or 0 equal to a. By using absorption law, we can write a dot a plus b equal to a, and a plus a dot b equal to a. So by using distributive law, we can write a dot b plus c equal to a dot b plus a dot c, and by using associative law, we can write a plus b plus c. This can be rewritten as a plus b plus c. So by using these kind of laws, we can reduce the Boolean functions. We will see the examples for better understanding. So consider this is the Boolean function. So this is a function of three variables x and y, x, y, z. So by using a conventional method Boolean postulates, we can reduce this function. So so consider these two literal. So here x bar is common, take x bar as common, will become y bar plus y plus x, y, z. So we know that so here we will see, we have already seen a plus a bar by using complementation law, a plus a bar equal to 1. So like that, y plus y bar will become 1, then it will become x bar dot 1 plus x, y, z. So we can, by using distributive law, we can rewrite this as x bar plus x and x bar plus y z, x bar plus y z. So we know x bar plus x will become 1, then we can rewrite as x bar plus y z. So this is the simplified function of given Boolean functions. So which requires 1, 2, 3 AND gate and 2 OR gate and 3 NOT gate. So in the simplified version, it requires only 1 OR gate, 1 OR gate, 1 AND gate, 1 AND gate and one NOT gate. So number of gate is reduced in the simplified version. So if number of gates is reduced, then automatically the area of the circuit will reduce, which automatically reduces the power consumption. So if the number here, there is only 3 input variable. If the number of variable progresses, and this Boolean postulates will become inefficient. It takes a lot more steps to reduce the function. It will take time, and sometimes it will lead to inefficient due to human error. So for that, to reduce the Boolean function, if the number of input variable increases, so one of the best method to reduce the Boolean function is K-map. So K-map is the pictorial representations where we can reduce the function by using the grouping. So we can group the adjacent ones by there are different grouping. We can group as a pair, that is 2 adjacent ones. We can group as 4 adjacent one, that is quad. It is called as quad. So we can group if there are 8 adjacent ones, which is called octet. We can group 16 adjacent ones. This is called hexa. So first we have to look at maximum possibility. If it is a 4 variable, we have to draw like this, and we have to look at there is a possibility of 16 adjacent ones. First we have to group that one. If there is no 16 adjacent one, then we have to go for 8 adjacent one. If not exists, then we have to go for 4 adjacent one. If quad is not possible, then we can go for parallel. This is the hierarchy to group minterms in the K-map. So in the given problem, there are different minterms, 1, 2, 3, 4, 5, 6, 7 minterms. So we have to fill the minterms into the K-map. So there are 4 variables. I have written A, B, C, D. So here we have to write 0, 0, 0, 1, 1, 1, 1, 0. So we should not write as 1, 0, 1, 1, because here we are using gray code in the K-map. So that is why we have to write 0, 0, 0, 1, 1, 1, 1, 0. So why we are going for gray code is the number of toggling in the gray code is less, which automatically reduces the number of switching. If number of switching reduces, then the power consumption will reduce. That is why we are designing the digital circuits by using gray code, not a normal binary number. So here this is the minterm A, B, C bar, D bar. So here A, B, C bar, D bar. So we have to fill here at 1. So next A, B, C bar, D, A, B, C bar, D. Here we have to fill 1. So next A, B bar, C bar, D, that is 1, 0, 0, 1. So 1, 0, 0, 1. Here we have to fill 1. So like that we have to fill all the minterms into the K-map. Now look at the grouping possibility. So here there are 3 grouping. So 3 quad possible. So this is the 1 quad. So this is the another quad. So this is the another quad. So expression for this function, this grouping is A, B. For this grouping, the expression is A. Here the common variable is D. A, D. For this grouping, A, C. So the final expression will become AB plus AD plus AC. So now look at the given function, reduced function. It has minimized to the extent. So both the function will give the same result. So if you implement this and design a logic circuit, and the reduced function, if you are implementing in the trainer kit, both will give you the same result, but the number of gates required to implement this original function, the reduced function, will vary. So it requires more number of AND gate and OR gate. It requires only three AND gates and 2 OR gates. 3 AND gates and 2 OR gates. So this is the benefit of reducing the Boolean functions, to reduce the number of literals in the given function, and which obviously will reduce the power consumed by this particular circuit. Thank you.